Today we are going to discuss about the mechanical rotational systems, an important topic under systems and their representation in control systems. So let us begin by recalling in simple. So want to differentiate translational and rotational system. So before understanding rotational systems, think about translational systems. In a translational system, we know that motion happens in a straight line. For considering an example, a vehicle moving forward or a piston moving inside a cylinder. But in a rotational system, motion occurs about a fixed axis in this example. So for including motor shafts, turbines, generators, flywheels and gear system. So the key difference between the translational motion is a linear motion. Rotational motion is an angular motion about an axis. So now let's explore the topics for discussion today. So introduction about mechanical rotational system with example, basic elements which are used in mechanical rotational systems, and mathematical modeling of mechanical rotational systems and their applications. So let's explore with a DT empathize part of mechanical rotational systems. So for this motor rotation, this is the motor torque and this is DC motor rotation, and the load torque will be generated in this rotation. So introduction about the mechanical rotational systems. Mechanical rotational systems involve rotational motion about an axis. So this is the rotational motion. This represents the action of rotation, and this is the angle of rotation motion in a disk rotation. Commonly used in motors, generators, turbines, gear systems and flywheels. So the mechanical rotational system governed by Newton's law for rotational motion. And the ideal elements which are used in the mechanical rotational systems are quantity and the standard symbol. The quantities are angular displacement, that is represented by V in radians, angular velocity, that is dV by dt radians per second, angular acceleration, it is d square V by dt square, the unit is radian per second square. Applied torque is represented as a T in Newton meter. Moment of inertia is J kg m by radians. Rotational frictional coefficient, that is B, and Newton meter per radian seconds. Stiffness of the spring is represented as K Newton meter per radians. The mechanical modeling DT empathize part, that is fundamental dynamic equation of mechanical rotational system is T of t is equal to J into d square theta divided by dt square plus B into d theta by dt plus K into theta. The physical interpretation of, that is J d square by dt square is torque needed to accelerate inertia, and B d theta by dt is torque lost due to damping, and K theta is restoring torque due to stiffness. And the mechanical rotational system around a central axis, the systems are commonly used in motors and everywhere. So in basic equation, considering torque equals the moment of inertia multiplied by the angular acceleration. That's why we represent it as a J into d square by dt square, where here the T is a torque and J is a moment of inertia and theta is the angular displacement. Understand the basic elements of mechanical rotational system, that is a moment of inertia, that is J, and it is represented as d square theta by dt square. So if we compare with the translational systems, this is similar to mass in translational systems. So it represents resistance to angular acceleration. So higher inertia means the system resists changes in rotational speed. Now let's coming to the B d theta by dt. This represents the friction in rotational motion. The damping torque is proportional to angular velocity. That means Td is equal to B into d theta by dt. So simple we can say that. So more speed gives the more damping torque. Next one is the K into theta, that is a torsional spring. This stores energy in rotational form. The restoring torque is proportional to angular displacement. So we can represent Ts is equal to K into theta. So more twist we can get the more restoring torque. So now let us combine these elements to form the mathematical model, that is T is equal to J into d square theta by dt square plus B into d theta by dt plus K into theta. And mechanical rotational systems widely used in, we know that DC motor and shaft control, robotics arm joints, wind turbines, electric vehicles, and gear mechanism, CNC machines, and etc. For example, in a DC motor, when the torque is applied to the shaft rotates about a fixed central axis, the shaft has inertia, friction, acts as a damping, and shaft elasticity behaves like a torsional spring. So the real-time system always combines these three elements: inertia, damping, and stiffness. And now come to the analogy part of one more one. This analogy is important for mechanical control systems. That is, force is represented as torque and mass is represented as the moment of inertia, and angular velocity is represented as the spring, and damper is represented as the rotational damper equation. So this analogy helps us convert mechanical system into electrical equivalent circuit for easier analysis. So let's summarize the today's session. We introduce with exploring part, that is a translational system and rotational system key differences. And we know that the examples of mechanical rotational systems and stiffness of the spring, moment of inertia, applied torque, angular displacement, and angular velocity. And we can form the transfer function T is equal to moment of inertia, velocity, and stiffness with an example, and the real-time examples of mechanical rotational systems. Now let's go for assessment quiz. So the first question is, in a mechanical rotational system, the damping torque is proportional to which one? The answer is angular velocity. The second question is, which of the following systems is best model as a mechanical rotational system in control analysis? DC motor shaft rotation. So the answer is option C for both the questions. Thank you.